Thank you very much. Thank you for this opportunity that I can do this presentation in the NICE workshop. Hello, everyone. My name is Florian Kelber. I'm currently a PhD student at the Technical University of Dresden at the HPSN chair under Professor Christian Meyer. In the next 20 minutes, I'd like to show you how we adapted the Spinnaker 2 architecture to be more performant for non-spiking neural networks, and how we actually map specific models on the Spinnaker 2 and check how fast possible it can be, and to reuse as much data as possible. So I also want to add a significant part of this work has also been done by a colleague of mine called Binji Wu. I did the paper in a joint fashion, so to speak. Okay, first off, I'd like to talk about the Spinnaker 2 at the start, where we are right now, what's in store for us in the future, and what was the past there a little bit. And the second part, I'd like to show you how we adapted the architecture, added the accelerator for matrix multiplication and 2D convolution. And in the third part, I go into detail how we actually map the model on the Spinnaker 2 architecture. So first off, we started the project since 2013 in close cooperation with the Manchester chair led by Steve Ferber since 2013. And over the past few years, we created prototypes of the Spinnaker 2 chip, which increased in features and also in better technology step by step. So now we are currently almost at the end. In 1.5 months to 2 months, the tape-out will be rolled out, and the Spinnaker 2 will be go into the fab. Afterwards, 2022, we also want to build up a 5 million core machine there, which will also stand here in Dresden. So the change from the first generation of Spinnaker 2, I think there's also a tutorial in this workshop here, so I can recommend it. And there are numerous of changes. First off, we used a better technology of 22 nanometer for better power consumption and for better performance, in the sense that we are now to increase the number of processing elements. As you can see here, PEs from 18 to 152, each with its own ARM. And for F-core, which means floating point, is possible now inside of the ARM core. We increased the frequency, so to speak, also the throughput, and included the faster and bigger DRAM for further applications, also considering artificial neural networks that are not spiking. Instead of one central point of communication, each PE is interconnected with each other on a 2D grid. That will be important later in a few slides. And also, as I said, we include numerous of accelerators, including many for neuromorphic purposes, like the random number generators and the exponential unit for ADX neuromorphic models, for example. We also included the accelerator for matrix multiplication and Conv2D, the MEG array. Let's dig in a little bit more into the current architecture that will be taped out, and also why we did the changes that we did. So first and foremost, artificial neural networks are great in a lot of specific tasks, and we also wanted to realize that on the bigger Spinnaker 2 model in combination with spiking neural networks. So our chair is also really interested in hybrid nets architectures, so to speak. And to realize bigger matrix multiplication and convolution tasks, of course, we want to not increase the Spinnaker 2 as much as possible right now. It was the dense architecture, because there are 152 PEs, and if you have a macro of a PE and you include something in there, it can blow up if it gets too big. So area was a big factor, and of course also we want to be as power efficient as possible. To get the most out of your buck, that you if you include something, you want it to maximize the frames per second as much as possible. Of course, be energy efficient as possible too. So we included the make array, and further investigated how to distribute the task on the many 152 PEs. So which means memory access from off-chip DRAM are more costly, as we all know, because of power reasons and of time reasons, of course. So we created some mapping and schedule strategies to avoid them as much as possible. Also, of course, for this mapping, we also, as one of the presenters said before, we also want to utilize everything that we have on the hardware to be as fast as possible. Also, the Spinnaker 2 has decoupled GALS, is the GLS architecture, which means global asynchronous, local synchronous, which also enables decoupled access execute order, in the sense that we can fetch data before it is really necessary to cut down time. And of course, because of this global asynchronous, local synchronous architecture, we are each PE is independent of each other, which means we have fine-grained control over the power and the frequency, so we can actually tune the power performance down if it's not that needed, which will also be important later. So this is the current architecture, which will be taped out. There are, as I said, 100. Do you see my mouse cursor?
Yes, we do.
Okay, great. Okay, thank you very much. There's a quad PE architecture. So this 2D grid has a lot of QPEs, which are consisting of 4 PEs, which are independent from another and are interconnected on the network on chip. They are all in this 2D grid, as I said before, and they can send messages to each other instead of only the router. Furthermore, we have chip-to-chip links that are here, which can interconnect to many other Spinnaker 2 chips, which is important, of course, because we are building a bigger core machine, which also routes over the Spinnaker router. Then we have a UDP interface with our own protocol to check to minimize data loss there and refetch if necessary. And of course, the LPDDR4 interfaces, as you can see here. And as I said before, each PE has its own MAC array, their accelerator, and each has its own ARM core, and each has also 128 kilobyte of SRAM. So we have a highly distributed system, which means there are a lot of memory SRAM banks that we have here, and we have the shared LPDDR4 that we have to consider while mapping. Let's go a little bit more into detail about the architecture of the machine learning accelerator. We decided to use 8-bit, 60-bit unsigned signed MAC array. In the sense, you can change the feature that you like, and it can use both for matrix multiplication and 2D convolution. As I said before, each PE has its own one, so which means they all need to be orchestrated in a nested parallelism manner. Furthermore, each accelerator has 2 inputs, either from it can fetch from the NOC or from the local SRAM, which means locally, usually we use the input feature map inside of the SRAM and fetch the weights, which are more mobile because they are smaller for convolutional case. We pre-fetch them before they are actually necessary, also on a micro scale in that regard, not only in a macro scale for the whole Spinnaker 2 system and the DRAM. Furthermore, for sparse networks, we have zero gating, which minimizes power use for that, and also an adder tree to reuse the 8-bit MAC cells that we have here, the 16x4, to combine into a 16-bit version, so to speak. The whole accelerator is output stationary, which means we don't need additional buffers before or after. That was a consideration because of the area that we wanted to avoid as much as possible. Also, it is output channel row stationary in the sense that instead of SIMD over the output columns output rows of the input rows, so to speak. We SIMD over the output channel, as you can see here, which allows us also for fully utilization for bottleneck layers or something else. Here we have the input feature maps, the kernels who get put in here and here, so to speak. And we also shift to reuse as much data we have inside of the accelerator from the input feature map side as possible. Also, it's a broadcast architecture, which means each of those cells get these outputs that are in here. They are getting multiplied and then added. And if all partial sums are finished, they get sent out into the SRAM that we have. So let's go a little bit more into the mapping. So of course, the problem, as we have with as all embedded designers for DNN architectures, is ANNs are pretty memory hungry. For example, there is for segmentic segmentation, the HRNet, which uses a ResNet 101 as a backbone. And ResNet, for example, the 50 version has a 12.41 megabyte, which doesn't fit in a 128 kilobyte. So we need to automatically divide it, of course. Also, as I said before, DRAM access is costly, so we want to avoid that by scheduling it. And yes, so what we did is we designed a Python parser, splitter, and distributor, which we call Spinnaker 2 Pi, which does this automatically and tries to map the layers into the Spinnaker 2 system with all the aspects I said before. So let's go a little bit into detail about that. The parser is there to get the model that we want to map, and does takes the computation graph of the whole network and does operator fusion. In a sense, it combines the output to the input to the next layer, so to speak. So we don't have to send it out into the DRAM and access back from the DRAM again into the Spinnaker 2 system. Afterwards, the computation graph is optimized. We split the task also to be hardware aware as possible, which means, as an example, the accelerator does a SIMD over 4 output channels. So we don't want to split under 4 channels as an example. And also we want to use all data lanes and all 152 PEs, which is important. Also, there are some pros and cons where you actually split in the dimension. And yeah, this is also part of what the splitter does. For the distributor, we want to reuse as much as data in a sense. So for on a QPE level, here are 4 PEs next to each other. First off is on the macro scale, so to speak, each input feature map gets combined with each kernel from the neighbor PE inside of one quad PE, so to speak. So each time step, they use the other from the neighbor. This is on the micro scale. However, we have 152 PEs that we all want to reuse the data that's in there. So we divided the Spinnaker 2 hardware into subsystems, which are the QPE blocks, which are 4 QPEs, and a double QPE block, which are 2 times the QPE block, so to speak. And each of those, if you go deeper and deeper inside, the memory fetch doesn't cost as much, so to speak. So we want to, reuse them, so to speak. Because of the nature of the filters, that they are much smaller and they're easier to transport in a sense, and also easier to split. So we do a data migration after each quad PE has each combination done. Then they get shared within each quad PE block, and afterwards inside of the double quad PE block, and then they get migrated to the next quad PE block. As you can see here, for example, here we have the data reuse on the smaller scale between PEs inside of a quad PE that we use inside of a quad PE block, where they all share the weights that the neighbor has. And then inside of the double quad PE block, and then also the data migration in a counterclockwise fashion in this regard, but it doesn't really matter. Furthermore, we also, when I was talking about, here is now important why I was talking about the fine-grained power control, we also can disable the ARM core and the accelerators to only, for example, reuse the SRAM inside of the PEs, which means if we have some problems considering the DRAM bottleneck, then it's easier to actually store the output of the layer that was computed in this time step, so to speak, from all of them inside of the storage QPEs and reuse them in the next step, basically. And we also did this for VGG16 and a ResNet. Here we have the roofline model for the ResNet 15. As you can see here, we have for the ResNet 15 all the convolutional layers and how they improved for attainable GOPS, so to speak, with data reuse and operator fusion, and it goes up. For fully connected, unfortunately, there's the problem because they're not computational hungry, but more memory hungry, which means the DRAM is a bigger bottleneck in this regard. So we could not attain that much for fully connected. So we are checking out how we can get to be more performant in this regard. But yeah, but in on itself, we created this accelerator with only a 7% increase in area for the whole Spinnaker 2 chip, so to speak, and with all accelerators attaining 4.6 TOPS per second. And yeah, as you can see here with the Spinnaker to Pi scheduling and mapping, we could increase the frames per second. As you can see here, the decrease in time of a frame by a factor of 3, as you can see here. The convolution was the most costly part, and we could reduce it a significant part. Next step is, of course, in the next month's tape out of the Spinnaker 2. And also we included for measurements from previous prototypes of the Spinnaker 2, we included the measurements inside of the Spinnaker 2 Pi, and also are now checking out new mapping and scheduling strategies to increase the power energy efficiency if the constraint of latency is reduced. So then we can just type in the latency that we wish to, and the Spinnaker 2 Pi automatically makes it as energy efficient as possible, considering that constraint. Also, we want to include further more complex models into the Spinnaker 2 Pi. So yeah, that's basically it. Pretty early, but thank you very much for your attention, and I'd like to have some questions.